Welcome to the Math 1, Unit 7, Lesson 8 summary video, Nothing Could Be Finer. This lesson is a practice understanding task which takes concepts you've been working on and applies them to new situations. The purpose of this lesson is to become fluent in representing key features of quadratic functions using multiple representations. Fairgoers can take home some official state fair souvenirs from the Nest in the Expo Center lobby. This year, the Nest has a new hat design to celebrate 150 years of the state fair, and they want to decide on a price that maximizes profit. The graph below represents profit, P of X, in hundreds of dollars generated by each hat price X. So we're going to be answering several questions, all relating to the key features of this quadratic function. A few things to make sure that we point out in the beginning is that the x-axis, this represents the price of the hat, and the y-axis represents the profit generated in hundreds of dollars. So when we see 154, we know that represents $15,400. So to review some of the key features of the quadratic functions, we know that we're looking for the x-intercepts, and we can see that this quadratic has two x-intercepts right here at 2, 0, and right here at 10, 0. And so if our x-intercept, if our x-axis represents the price of each hat, we know that this x-intercept represents a cost of $2 per hat, and our y-axis represents the profit. So that means if the company charges $2 per hat, then they aren't going to make any profit. And this other x-intercept represents the $10 price per hat, again resulting in zero profit. We can see that our maximum is here. This is our vertex, and it's represented by the point 6,154, which in the context of this story tells us that if the hat costs $6, if each of the hats cost $6, then they would expect to make a profit of $15,400. Again, we notice that the vertex is at when x is 6, which is halfway between my two x-intercepts, the x values of those x-intercepts. So 6 is halfway between 2 and 10. This, if I were to draw a line straight down, that would be my axis of symmetry. It's saying that my quadratic is symmetrical about this axis. We see that our y-intercept is way down here, and it's got a negative y value. Again, if our y-axis represents the profit, then what that tells us is that if they charge $0 per hat, or they give them away for free, they're actually not going to make any profit. They're going to be spending money to make the hats without gaining any income. So they would end up losing, remember this is in hundreds of dollars, so they would end up losing $19,250 if they gave all the hats away for free. So we can see that on this left side of the quadratic, it's increasing. We know that it's only relative as far as profit goes. Profit is anything above this x-axis. In order for the company to make a profit, they've got to be in the positive numbers for their profit. So the interval of increase here from 0 to 6 is showing, from 2 to 6 is showing the company increasing their profit. And then we can see from 6 to 10, that's $6 per hat to $10 per hat, they are decreasing their profit. They're still making money. It's not until they go below the x-axis that they're no longer making money, but they are not making, as their profit is decreasing with every dollar that they increase the price of the hat. And this is similar to one of the previous lessons that we looked at. Because at the x-intercepts, the y values are 0, indicating that no profit is being made, we know that just above 2 or $2 per hat is where the company would start to make a profit. So the smallest value that they could sell the hat for above $2 would be $2.01. That would be the cheapest or the minimum price that they could sell the hat for and still make a profit. And they would make that profit all the way up until they would continue to increase their profit up to $6 per hat. So if we look at the portion of our graph, this relative domain here for profit from 2 to 10, we can tell that the range for that portion of the graph would be from $0 being made all the way up to $15,400 being made. And if we think back to lesson 6 with the concert ticket prices, this is a similar scenario. Just because we charge more for the price of the hat, if we charge anything above $6, our profit is going to decrease. And so just because we charge more doesn't mean that we're actually going to make more money. And when we look a little closer at this y-intercept of negative $19,250, we can assume that that's the cost of printing the hats. So that's how much it's going to cost them just to produce the product if they were to give it all away for free. And finally, if we explore some of these intervals a little more closely, we can determine between which intervals the profit is increasing the fastest. So if we look between the interval of 2 and 3, or $2 per hat and $3 per hat, it's going from a profit of $0 up to about $6,000. And if we look from 3 to 4, it's going from about $6,000 up to, that's 1,000, so up to about $1,200. And if we look between the interval of 4 and 5, it's going up about $200. Now keep in mind that because this is symmetrical, there are actually 2 price points where the company will make the same profit, all except for the vertex, of course. And so just as we saw with the x-intercepts, if they charge $2 per hat or $10 per hat, they're going to make 0 profit. And we can see if they charge $3 per hat or they charge $9 per hat, again, it's going to have that same y value at each of those points. And so that indicates that they're going to be making the same profit whether they charge $3 per hat or $9 per hat. In the second part of this task, you're being asked to match each quadratic function, the graph, with the appropriate equation. And while we haven't done a lot of exploring or focusing on the equations in this unit, we will dive deep into that during the next unit. So all we really want to get out of this portion is just kind of making some observations and using those key features of the functions that we've been exploring throughout this unit. And so if we look at graph A, we can tell that there's an x-intercept right here at -2, when x is -2, and there's a x-intercept here where x is positive 2. We can tell that the y-intercept is here at positive 4. When we look at graph B, we can see that the y-intercept here is at negative 3. We can see that the x-intercepts are at negative 1 and positive 3. And if we look at graph C, we can see that the y-intercept is at negative 9. Oh, excuse me, that's 8. And the x-intercepts are at negative 4 and positive 2. And so if we look at the equations and we just kind of focus on the x-intercepts, we see the x-intercepts here are negative 2 and positive 2, negative 1, positive 3, negative 4, positive 2. If we look for values that are similar in our equations, we can see that with the negative 4 and the positive 2, we have the opposite values here in equation 1. And the negative 2 and positive 2, well, we have those exact ones here. And negative 1 and positive 3, well, we have two of those here. We have a negative 1 and a positive 3 here, and a positive 1 and a negative 3 here. So if we look back to C, when x is negative 4, the x-intercept is negative 4 and positive 2. Notice how we have the opposite value here. And this is our zero product property, which we will also explore more in Unit 8. But basically what it's saying is that if we set, we know that our x-intercept, when we have an x-intercept, our y value is going to be 0. So if we were to set this y value to 0, that means that because this binomial and this binomial are being multiplied together to equal 0, that means that either this factor or this factor has to be 0. And so what we can do is actually set each of these equal to 0. And then using our properties of equality and inverse operations, we can solve for x. And so here we find that x is negative 2. Excuse me, positive 2. And if we did the same thing for x plus 4 equals 0, and we subtract 4 from both sides of our equation, then we get x equals negative 4. And so we can see then that these are our x-intercepts right here. And so if we were to look for the same pattern here for B, a negative 1 would be x plus 1. That would be my factor. And a positive 3 would be an x minus 3 as a factor. And so if we look over here, the x plus 1 and x minus 3, that would be the fifth equation. And here, this would be x plus 2 would be my first factor, and x minus 2 would be my second factor. So x plus 2 and x minus 2 would give me equation 2. So we know that these are the three equations that represent these three graphs. And if we were to multiply our two factors, our two binomials together, you can see how I did that for the first three equations down here. We would get this equation. And again, we said that this was problem number 2, and this was problem number 5, and this was problem number 1. So if we look at problem number 1 and number 2, one thing we notice is when I simplify this all the way down, I have a -8 here as my constant. And just like in my linear functions, the constant is my y-intercept. And so when we look at the graph for letter C, we already established that my y-intercept here was at -8. And if we did the same thing for problem 2, our y-intercept is at +4. So that's another helpful feature that we can look at when we're trying to match an equation with a graph, or write the equation from the graph, or graph the equation. And so one other thing that we want to look at is the fact that this first term in my trinomial because it's got 3 terms. This is a binomial because it's got 2 terms. In this binomial, my first term is negative, whereas in the first equation, it's positive. And we can see that outside of the first factor, there's nothing here, so that's understood to be positive. Whereas for problem number 2, we see that there's a negative outside here, or a -1, which you can see that we distributed to, after we simplified, we distributed it to each of these 2 terms inside the parentheses. And so what we also notice when we look at these graphs is that some of them have a maximum vertex, meaning the highest point is their vertex, the highest value, and then some of them have a minimum. And this means that the vertex is down at the bottom of the parabola. And so a quadratic that has a maximum means that it's opening downward. And a quadratic that has a minimum means that it's opening upward. And so when we look at problem number 5, also equation number 5, we see that this one is positive. And so both graphs B and C have a minimum, and their matching equations, equations 1 and 5, both had positive values outside of the first 2 factors. And even when we simplify it, this is standard form, even when we simplify it into standard form, our first term is positive. So what that leads us to understand is that if there's a positive number outside of these 2 factors, or in standard form, if the first term is positive, then the quadratic is going to have a minimum, a vertex that is a minimum. And if it is negative, then it's going to have a maximum value. And so with that information, you should be able to match the remaining graphs with their equations.